Kia ora, and welcome to a lesson on Cambridge Mathematics differential equations. So, you may be thinking, I've seen differential equations before, and you'd be right. So, because a differential equation is an equation that is just written as something like dy by dx is equal to 3x squared. And dy by dx is called a first order differential equation, because it's the first time that you've differentiated it. If I was to differentiate dy by dx again and get d2y by dx squared is equal to 6x, this is considered a second order differential equation. What we're going to be doing today is going from first order differential equations to general solutions and particular solutions. So a general solution is just where you take dy by dx and take it back into its form y is equal to, okay, via some form of anti-differentiation integration method. Okay, so if I was to take dy by dx and transform it into its y is equal to form, I'd get y is equal to x cubed plus c. Okay, this is called the general solution because I've got plus c. If I was given some values, such as a point on which the line y equals x cubed plus c goes through, such as 0, 0, if I know it goes through 0, 0, and I write the form y is equal to x cubed, because that satisfies going through a point y equals x cubed, that is called a particular solution. Okay, so these are just some terminology things to know about. Okay, and they're going to be referenced throughout. So, we've been going from first order differential equations to general solutions and particular solutions since P1. Okay, but let's see what we're actually doing when we do that. So if I have another equation, dy by dx is equal to 6 lots of x plus 1 squared. Okay, if I'm taking this to its general solution or its particular solution, what I am technically doing is integrating both sides of the equation with respect to dx. So let's have a look at what that looks like. So I'm technically integrating dy by dx with respect to x, and I'm integrating 6 bracket x plus 1 squared also with respect to x. So on the left hand side, things cancel out, which just gives me the integral of dy is equal to the integral of this, which using chain rule, add 1 to your power, divide by the differential, is going to give me 2x plus 1 cubed plus c. I also know that the integral of dy is just y, because it's basically the integral of 1 with respect to y, which is why it becomes y. So let's just put that slightly the same. The integral of 1 with respect to y, which just becomes y, and the other side is just 2x plus 1 cubed plus c. And given a point, I can then use this to find out what the c might be for a particular solution. So what we can say is that if you've got an equation such as, let's change it to this color, the function y dy by dx, and you integrate this with respect to x, then what you are left with is the integral of a function y with respect to y. Okay, this is useful because it's going to allow us to look at some more complicated cases, because we've looked at this since P1, as I said, and you've never really thought of it this way because it's just, oh, go from dy by dx to y equals this. However, knowing what's actually going on and knowing this part in particular will allow us to differentiate more complex, integrate more complex differential equations, such as dy by dx is equal to x, y. Okay, we've not looked prior to this point at how you would integrate a differential equation such as xy where there's a term involving y. What we have looked at previously is how you would differentiate terms involving y with our parametric equations. So what we actually need to do here is set it up so it's almost like a parametric equation, get y to our left hand side with the dy by dx. So this would become 1 over y dy by dx is equal to x. And then when we integrate this with respect to x, this is what we get. We get the integral of 1 over y dy by dx with respect to x is equal to the integral of x with respect to x. Well, as we saw a second ago, the dx's cancel out here, so what we're actually doing on the left hand side is integrating 1 over y with respect to y. And 1 over y, when integrated with respect to y, is natural log y. And the integral of x with respect to x is x squared over 2. If we're wanting this to be in the form, both sides should have a plus, shouldn't they? If I integrate this side, I should get plus a, and this side plus b, which can just then rearrange into a form log y is equal to x squared over 2 plus c. Because a and b are both constants, when put over to one side, we can consider it just an overall constant. So you don't need to worry about the fact that there's two different constants, because at the end of the day, it's just going to form one thing. However, I want this to be in the form y equals, so I need to do a slight bit more work to get in the form y equals. So I'm going to take e of both sides, which gives me, well, e to power log y is just y, and then the other side is e x squared over 2 plus c. Bit of power laws here, so if I have adding powers, what I can say is that's the same as having e to the x squared over 2 times e to power c, and I can consider e to power c another constant, because if c is just a value and e is just a value, then e to power c is just a value. So I can say that's e to the x squared over 2 times, let's call it d, which can be written as d e to the x squared over 2. And given a value, I could find out what d is equivalent to. I was given like an xy coordinate, but I'm not going to focus on that now. But this is just the general solution. Okay. And like I say, I could find a particular solution given a value of x and y. So the key points to take away here is to rearrange this function, the original differential equation, so that y is with your dy by dx, so that when you integrate with respect to x, these cancel out, so that you can integrate just purely with respect to y, and integrate the other side with respect to x. Constants form one constant, and then doing whatever form of rearrangement you might need to do to get it so that's y equals. It won't always be logs, it can be other things as well. Let's have a look at an actual example here. So the variables x and y satisfy the differential equation dy by dx is equal to 1 plus x over 2y. It is given that y equals 3 when x equals 0. Solve the differential equation and obtain an expression for y in terms of x. So step 1, get the 2y to the other side. So I'm going to end up with 2y dy by dx is equal to 1 plus x. I'm trying to get to a particular solution here, so I'm integrating both sides with respect to x. So integral of 2y dy by dx with respect to x is equal to the integral of 1 plus x with respect to x. Again, things are going to cancel out. Dx and dx will cancel. So I'm integrating with 2y with respect to y now, which gives me y squared. And that is equal to x plus x squared over 2. Again, I have plus a on the left and plus b on the right. So I'm just going to cut out the middleman doing the rearrangement and just say plus c. Going to take the a over to the b straight away and not really worry about that. So I get plus c. Okay. I know that when y is equal to 3, x is equal to 0. So I'm going to just substitute that in now to find out what my c is. So I get 3 squared is equal to 0 plus 0 squared over 2 plus c. So c is just equal to 9. I'm going to put that back into the equation, which is y squared is equal to x plus x squared over 2 plus 9. And because I just want it in terms of y, I'm just going to get rid of a y square by square rooting. X plus x squared over 2 plus 9. Okay, which I could write as a power half instead, but I'm just going to leave it as a square root. Okay, that is the particular solution for the question that was given to you. Okay, let's have a look at another question. Example 2 is given that for x is greater than 0 at less than 300, dx over dt is equal to x 300 minus x over 600 and x equals 50 when t equals 0. Find the particular solution of a differential equation, giving your answer as an expression for x in terms of t. So, we've now got dx over dt. Think of this as dy over dx. When it was dy over dx, we need to get our y terms to be with our dy over dx. So when it's dx over dt, we need to get our x terms over to the same side as dx over dt. So step 1 is to rewrite our equation as 1 over x 300 minus x dx over dt. That is equal to 1 over 600. So all I've done is divide down from the x 300 minus x to be 1 over 300 minus x. Or another way of thinking of it is dividing through by x 300 minus x. Now I'm going to integrate this with respect to t so that we get an equation in terms of x's and t's. So again, I'm going to show the full writing for this. So we're going to integrate 1 over x 300 minus x dx over dt with respect to t, and we're going to integrate 1 over 600 with respect to t. Cancel, 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 integrating with respect to x. This is going to be hard. We can't just straight away integrate 1 over x 300 minus x with respect to x. We need to split it first into partial fractions. Right hand side, integrating 1 over 600 with respect to t is easy because you just chuck a t on there. So let's quickly just do 1 over x 300 minus x into partial fractions. So that is the same as saying a over x plus b over 300 minus x, which is the same as saying 1 is equal to a 300 minus x plus b x. Substitute a value in, so x equals 0, giving you 1 is equal to 300a, so a is 1 over 300. Okay, when I substitute in b is when I substitute x equals 300 into this, I get 1 is equal to 300b. So b is also 1 over 300. So my partial fraction will be 1 over 300 over x plus 1 over 300 over 300 minus x, which can be rewritten as 1 over 300 times 1 over x plus 1 over 300 minus x. Sorry for the messiness on my right, just running out a bit of space there. Okay, so when I come back to this equation, 1 over 300, 1 over x plus 1 over 300 minus x, integrating with respect to x, is equal to the integral of 1 over 600 with respect to t. Because this is a scalar multiplication here, I can actually just move that to the before the integral. So all I'm going to be doing is 1 over 300 integral of 1 over x plus 1 over 300 minus x dx, and that is equal to the integral of 1 over 600 dt. So a bit of faffing around there to get rid of my to change my fraction into partial fractions, but now I can integrate this, giving me 1 over 300 times, well, 1 over x integrated with respect to x is just log x, natural log x, plus the natural, oh sorry, not plus, because when I integrate the 1 over 300 minus x, I need to divide by the differential of 300 minus x, and the differential of 300 minus x is minus 1. So this becomes minus log 300 minus x as a single identity. You've got to be pretty good at your other integration stuff with this and differentiation stuff. This is definitely the last thing you need to be learning in terms of differential equations before P3, and you do need to be comfortable with everything that comes before. I don't have time to really go over every aspect, so maybe go back and have a look at some stuff if you're not quite following along with this. But the integral of 1 over 600 with respect to t is just 1 over 600 t plus c. Okay, never forget your plus c. Always remember plus c. Okay, tidying up to do. I'm going to get rid of this by timesing through by 1 over 300. Okay, well, timesing through by 300. I want to get rid of that 1 over 300 in front of this log x situation, so I'm going to get log x minus log 300 minus x is equal to a half t plus, again, still c, because timesing c by 300, yes, it does make it 300c, but still just a constant until I actually find out what it is. So don't worry too much about saying, oh, that's 300c now, and because it's going to be 300c throughout until the end, so there's not much really to work with. Some tidying up to do with our logs, so just using some log laws. If you've got log minus log, you can say that's as log divide, so we get log x over 300 minus x is equal to half t plus c. At this point, it's possibly a good point to work out what our c is. So our c is going to be whatever our answer is when we substitute in 0, x is 50 and t equals 0. So t equals 0, meaning right hand side is just going to be 0 plus c anyway. But we get log 50 over 300 minus 50 is equal to half log of 0 plus c, which is going to give you a c value of log 0.2. We can put this back into our equation. Log x over 300 minus x is equal to half t plus log 0.2. But because we want this in terms of x in terms of t. We still need to do some rearrangement here to get this to be an x equal. So we need to get rid of natural log. So to get rid of natural log, we're going to take exponentials. So x over 300 minus x is equal to e to the half t plus natural log 0.2, which again can be split as e to the half t times e to the natural log 0.2, which when you consider what e to the natural log 0.2 is, well, the e and the log cancel each other out, just giving you 0.2. So this is e to the half t times 0.2. Okay, so this x over 300 minus x is equal to 0.2 e to the half t. Let's just check that. Yes. Okay. Still, this is not x equals, so we need to do a bit of rearrangement. So we're going to times up by our 300 minus x to get 300 minus x times 0.2 e to the half t. We're going to expand out our brackets and get 300 times 0.2, which is 60, e to the half t, minus 0.2 x e to the half t. We're going to take our terms involving x to one side to get x plus 0.2 x e to the half t, which is equal to 60 e to the half t. And then we're going to factorise our x out of this to get 1 plus 0.2 e to the half t is equal to 60 e to the half t. And then we're going to divide through by that to get x equals 60 e to the half t all over 1 plus 0.2 e to the half t. So a bit of algebraic manipulation there to get from x over 300 minus x to x equals. But there we go. So this is how we can go from our initial differential equation to our particular solution. Okay, let's have a look at one more, and this one involves a fairly annoying, tricky bit. So we're going to find the general solution of a differential equation x squared plus 1 times y cubed plus x squared dy by dx equals 0. So the first thing you might notice when looking at this is it's not written in the normal way. It's not written as dy by dx is equal to something. It's written with everything on the left hand side. So we need to do some rearrangement first. So we need to get this so that the y is with the dy by dx and everything else is on the opposite side. Okay, so the first step we're going to take is we're going to say x squared dy by dx is equal to negative x squared plus 1 y cubed. Then we're going to do a bit of swapping around. 1 over y cubed dy by dx is equal to minus x squared plus 1 all over x squared. Okay, so one of the things that we need to understand here is that when we're integrating, we have to assume that y cannot equal 0 because we've got 1 over 0 here. And theoretically also x equals 0, but mainly the y cannot equal 0. And that's going to play into part later on. Okay, so first thing to do is simplify down the right hand side and the left hand side. Okay, we're going to say that 1 over y cubed is actually just y to the minus 3 to make it easier to integrate, dy by dx. And we're going to say with our left hand side that x squared divided by x squared is just minus 1, and minus plus 1 over x squared is the same as saying minus x to the minus 2. And then we're going to integrate both sides with respect to x, dy by dx, minus 1, integral minus 1 minus x to minus 2 dx, cancel, integral of y minus 3 with respect to y, add 1 to the power, divide by your new power, giving you y to the power minus 2 over negative 2, so minus 2, which is equal to the integral of the right hand side with respect to x. So again, add 1 to the power, divide by new power, we get minus x. That becomes minus 1 divided by minus 1, so plus x to the minus 1 plus c. Okay, this is a general solution. It's not a general solution in terms of y in terms of x, but it's not specified in the question to be y in terms of x, but this is a general solution. You could go through this and then with rearrangement get it so that's a y equals general solution, and the question may want you to do that in future, so just be wary that this is technically a general solution, but it's not the general solution when it's y in terms of x. As I said earlier, this y cannot equal 0 situation is important now. So here we've stated that y cannot equal 0 for us to work because 1 over 0 is undefined. Okay. However, when you consider the solution of a graph of y equals 0 is just the line that runs along the x-axis. Okay, just this line here. Okay, could it be a solution to this differential? Well, if we what is a gradient if we are running along the x-axis? Well, the gradient is 0. So if dy by dx is equal to 0 when y is 0, then we must assume that y is equal to 0 is actually a solution giving to this equation, which is confusing. So let's have a look. Does this work? Well, when I rearrange this equation here, so that's just dy by dx, I get dy by dx is equal to minus x squared plus 1 y cubed over x squared. Okay, so just rearranging this to here. If y is equal to 0, then dy by dx becomes 0 divided by x squared, and for any value of x, this would be 0. Okay, because 0 divided by anything is 0. So our solution y equals 0 is actually valid, even though in our previous differential equation it couldn't be valid for that particular situation. So there's two solutions to this question, which is either y is equal to what we created a second ago, not y, our general solution being 1 over 2y squared is equal to 1 over x minus x plus c. That was for when y cannot equal 0, or our other solution, which is just y is equal to 0. Okay, those are our two general solutions. So if there's ever a point where you have to eliminate a solution, such as y being equal to 0, you do need to test it with these to see whether it would still produce a valid solution. And if it does, you then need to include it as one of your valid solutions to the question. That's confusing. That's going to be one of the things that's harder to do. But just be wary that something like that could come up. Hopefully you've understood this and you think you can have a go at some questions that are similar to this now. Good luck, and I'll speak to you again soon. Bye.